Hi, good morning, students. Today we are discussing a new chapter. We are starting the chapter Work, Energy, and Power. See, in many situations we have heard about a lot of works, different types of works we have heard. Home work, kitchen work, and always we are busy with different types of works. So, actually, what is work in physics? See, in the case of a person standing in front of the gate as a security or a gatekeeper, he is just standing at the gate. We say that he is doing his work. At the end of the month, he is getting his salary. And you are saying that you are doing some homework. But in all respects, this is not a physical work. In physics, work is said to be done only when there is a force applied and there is certain distance or certain displacement in the direction of that force applied. So force is said to be, work is said to be done by a force if there is a force applied and the object or the point at which the force is applied is is followed some displacement in the direction of that force applied. So work is said to be done only when force is applied and the body moves through some amount of distance in the direction of that force applied. Okay, so pushing a car, drawing a table, these all are physical work. So what are the necessary conditions for doing a work? First one, force. A force must be acted on the body, and the point of application of the force must move in the direction of that force applied. Okay, so necessary conditions for a physical, work is said to be done is that first one, a force must be acted on the body. Second one, the point of application of that force must move in the direction of that force applied. Okay, now how to express the magnitude of force applied? See, let us consider that uh, expression for work done. See, this is the object. It is there on a horizontal surface, and here a force is applied. A force F is applied. So the body displaces to another point. So now, what is displacement? The object is applied with the force at this point A. Now the point A reaches to another point, another orientation. So the displacement of the point of application of forces, yes, it is this much. This point moved to this point. So this is the point of application of force. It is displaced by this much. Now here the force and the displacement are displacement are in the same direction. Both the force and displacement are in the same direction. So the work done equal to magnitude of force into displacement in the direction of that force applied. So if the force and displacement are in the same direction, work done will be equal to the product of magnitude of force and the displacement in the direction of that force applied. But in normal situations, the force applied and displacement may not be in the same direction. So, for example, you are drawing a table or you are pushing a car. At the time, there is an inclination between the direction of force and the displacement of the body. That is, here it is the car. and here you are pushing the car. Here you are pushing the car from here. So what happened? The direction of force is along this direction, and the displacement is along this. So the displacement and force are inclined by certain angle. Okay, so when we are drawing trolley carrier, etc., where the direction of force and the displacement are inclined. At the time, if this is the angle theta between direction of force applied and the displacement of that point, we are finding the work done as the component of force, F component, force component in the direction of displacement multiplied by the magnitude of displacement. So when the force is inclined at an angle theta with the displacement, we have to express the work done as work done equal to the product of force component in the direction of displacement multiplied by that displacement actually it has. So here the work done equal to, what is the component of this force in this direction of displacement? F and theta, they are having some adjacent relation, that means cosine component. So we can write the component of force in the direction of displacement is F cos theta. The component of force vector along the direction of displacement is F cos theta into the displacement is S. So we can write it as W equal to Fs into cos theta. Force applied is F, displacement suffered is S, and the angle between directions of force and displacement is theta. Then W equal to Fs cos theta, or W equal to F dot S, we can write so. Why? Being force and the displacement are vector, this is dot product of the two vectors, Fs cos theta. Now we have to express the unit of force. What is the unit of force? What is the unit of work done? See, we are discussing the unit of work done. We have written W equal to Fs. Here, this is force which is measured in Newton and displaced in the unit of meter. So we have the unit of work done equal to Newton meter, but actually the SI unit of work done is joule, where 1 joule equal to 1 Newton meter. If a force of 1 Newton is applied on a body such that it is displaced by a displacement of 1 meter, then the work done is 1 joule. So 1 joule equal to 1 Newton meter. If a force of 1 Newton is applied on a body such that the body displaced in the direction of force by a magnitude of 1 meter, then the work done is 1 Newton meter, which is equal to 1 joule. 1 Newton meter is equal to 1 joule. Now we can convert this Newton meter into our dyne, the CGS system. We have 1 Newton. Once we have discussed, 1 Newton is 10 raised to 5 dyne, and 1 meter is 100 centimeter. So 1 Newton 10 raised to 5 dyne, then 1 meter 100 centimeter. Then we can write 10 raised to 7, 5 and 2, 10 raised to 7 dyne centimeter is equal to 1 joule. So 1 joule is 10 raised to 7 dyne centimeter. So we have expressed the expression for finding the magnitude of work done by a force. Actually, in that situation, the force is very constant. In our previous expression, W equal to Fs cos theta or W equal to F dot S, where the force is constant, means the force magnitude remains the same with any change in time. Whenever the body is experiencing the force and that force does not change with the time, then we are said it is a constant force. Throughout the event of application of the force, the magnitude of force remains constant. So it is a force, it is a constant force. But now we are discussing about work done by a variable force. You just imagine you are launched a rocket from the earth's surface, it is going up, and we can see that with the height or with the distance the rocket has launched, we can see that the force experience will be different. The force will be decreasing, or there will be a change of force magnitude with the time. Similarly, when you are throwing a stone, with the time it has traveled, we can see that the magnitude of force it has experienced, it is affected, is decreasing or it is changing. So a variable force is that force which is in such a way that the force acted on the body is varying with the time. If the force acted on the body is varying with the time, it is a variable force. It is not a constant force. Then another example, you just imagine you are compressing a spring. You are given an helical elastic spring. When you are compressing the spring, with the time it has experienced the force magnitude is changing. So the force at different extent of displacement is different, then it is a variable force. The magnitude of force acted on the body varies with the time, then it is a variable force. So we are writing variable force as Fx. With the displacement, the force value is changing. So that is a variable force. Now we are discussing about how to find the work done by a variable force. We are plotting a graph showing the variation of force with displacement. See, variable force means its magnitude is different at different extent of displacement. So if x is the displacement, the variable force is Fx, then we can get a curve where with the displacement the force magnitude is changing. At the time, how to find the work done by the variable force? See, let this be the initial displacement and let this be the final displacement. So under this curve we can make so many rectangular portions. This graph is changing the initial value of displacement xi to xf. So in between we are getting a small strip of rectangular portion. The area of the rectangular portion will be equal to a small displacement that will be equal to dx. In between this initial and final displacement, that the short displacement where it is very close to 0, the dx is very small, then the area equal to, this is the Fx value, the variable force corresponding to that short displacement, Fx into displacement is dx. So area equal to Fx into dx, and you can see that this is the product of force and displacement, and this will be equal to the amount of work done for a short displacement of dx. The small amount of work done to have small displacement dx by the variable forces Fx into dx. Now we can see that to get the total work done from initial to final displacement, we have to find the area under this graph, area under the force displacement graph. So to get the total work done, we are finding the sum of these small areas, which is equal to the work done by the variable force for a short displacement. So how to find the sum of this area? We are finding the integral value of xi to xf, the area Fx dx. If Fx dx is a small area of the small rectangular portion, to find the total area under the graph, we are finding the integral xi to xf of the small areas. So this will be given the total work done. So work done by a variable force can be equal to the area, the total area under the force displacement graph. Okay, and mathematically it is the integral limit changing from initial xi to final xf Fx dx, where Fx is the displacement, Fx is the variable force and dx is the which one, displacement in that short interval of time.